All right, how do I do this again? Aha. Okay. Can everyone see the presentation?
Yeah, we see it very well.
Okay. Yeah, so thanks, Murray, for the lovely introduction. Yeah, I'm going to talk about Bragg Creek today. I grew up right near Bragg Creek, actually, so from a small hamlet next to it called Priddis. And I don't know much about the geology of Bragg Creek, so it's a little bit of a personal learning experience for myself as well. So here we just have a photo from a lovely little lake near Bragg Creek, but Bragg Creek's not so much in the mountains. This is just next to it. But, oh, why won't it let me change? Aha, there we go. Okay, so Bragg Creek is a small provincial park in the foothills of southern Alberta. So it's about 20 minutes southwest of Calgary, so just east of the Kananaskis country. And it's just before you start getting into the mountains. So more so rolling hills, not so much exposed rock. So in the Google Maps image, you can see Edmonton as the blue dot and Bragg Creek down here is the red dot. And then a lovely little aerial photo of Bragg Creek. So you can see it's quite a small town. It's actually a hamlet, so less than 600 people in the place. And it's quite forested and again, gentle rolling hills as opposed to sharp mountainous terrain. So a little bit of a factoid, Bragg Creek is named after Albert Warren Bragg from Collingwood, Nova Scotia, and his 14-year-old brother who homesteaded the area in the late 1800s. And presently it's used as ranch lands, as well as the provincial park itself is more recreation. And then there's the Tsuut'ina and Sarcee Indian reserves next to it as well. Getting into the geology, the red stars represent where Bragg Creek is on these maps. So it's in the Rocky Mountain foothills, so just in the foothills of the fold and thrust belt, just before you get to the prairies. And it's dominantly shallow thrusts and folds, so not so much the sharp thrusting that you see down here in the mountains. So Bragg Creek's over here in these Cretaceous rocks. Yeah, and it's dominantly, the subsurface is mostly Cretaceous rocks. Yeah, and then we have quaternary glacial deposits overlying some of these rocks, but mostly it's the Cretaceous rocks in the subsurface of the rolling hills. And because it's not as cliffy as some of the mountains, it's not got as many exposed outcrops. So mostly vegetated areas, but you do start to see some of these little erratics throughout. Yeah. And then just a little bit of a closer up image here of all the thrust faults in the area. So again, Bragg Creek is down here where this little one is, which represents this little starred area here. The formations that are present in the area, again, mostly Cretaceous. You can see kind of that thrusting and folding through these anticlines and synclines over here. The cross section on top, A to B, is represented by this black line here, and Bragg Creek again is the starred section there. So you've probably heard some of these formation names before, but the dominant outcrops in the area are the Belly River, the Upper and Lower Alberta Formation, the Blairmore Formation, and the Cardium Formation. And then a little picture down here showing more so the vegetated hills, not so much the outcrops, but in the subsurface you can see kind of the thrusting of all of these Cretaceous deposits. A little bit about the economic geology of the area. We have a couple gas fields right next to Bragg Creek. So there's Quirk Creek gas field, which is about 20 minutes south or 20 kilometers south. It produces from the Mount Head and the Turner Valley carbonates, so Mississippian carbonates. And it's got 3 thrusts that produce from both formations. So the little inset here shows the 3 thrusted sheets, sheet A, sheet B, sheet C, and then both the Mount Head and Turner Valley present in each, which it produces from. And then the Moose Mountain gas field as well. So the image down here, this is a picture of Moose Mountain from above. Down here we have a picture of the gas plant. And it also produces from the Turner Valley Formation. Moose Mountain itself is thrusted Mississippian carbonates exposed at the surface, whereas the gas field is just south of that mountain in a thrust below. And Moose Mountain is about 30 kilometers northwest of Bragg Creek, so gas fields kind of surrounding the area. And then as well, we have quaternary deposits, so some mineable aggregates. This is an aggregate map surrounding Bragg Creek. So Bragg Creek is in this little square here, and we have quite a few different aggregate deposits. So they're formed from glacial fluvial terraces. So that's represented by the one here. So this whole area here was a paleo terrace, and then fluvial terraces represented in this whole area by number 2, and then channels, glacial channels in number 3. So definitely a lot of economic geology around the area. Not so much exposed rocks, but you can go to the mountains to see some of those. And then a little bit more modern geology. I'm sure we all remember the floods in Calgary in 2013, or at least I do, because I'm from there. But we heard about Calgary, we heard about Canmore, you heard about High River. There was not so much news about Bragg Creek, but of course Bragg Creek is adjacent to the Elbow River, which eventually connects to the Bow River, which is the one that flooded Calgary. And so there was significant flooding in Bragg Creek. As you can see, some of the damage to the homes that were right adjacent to the creek here. A lot of irreparable damage still to this day that hasn't been fixed, as well as pretty much the whole town was underwater. The river flooded its banks, and it's kind of got a new channel formed now. And as well, in Bragg Creek Provincial Park, so right next to a popular waterfall called Elbow Falls. These are benches that were on the banks before the flood, and now they are in the channel. So it's definitely, you can see the size of the boulders here and kind of picture the amount of water that must have come through the town to be able to do that. It's pretty darn impressive.
That's pretty cool.
Yeah.
I think the water would have to be flowing at about, I don't know, 10 meters per second to push boulders that big.
Yeah, it's just crazy. Like, imagine there was nothing there before, and then, oh, pretty much devastated the entire area. And then, why would you go to Bragg Creek? It's a relatively small provincial park compared to some of the bigger ones like Banff and Jasper, and of course it's not in the mountains, but it has its special benefits. Probably one of the most popular areas in Bragg Creek is Elbow Falls, so a small waterfall. You can see the Cretaceous sandstones here cropping out. As well, you have Prairie Mountain. So they have a lot of these smaller mountains, maybe just baby mountains, but they're great for hiking, especially in the winter when the bigger mountains in the Rockies are inaccessible. So you can hike Prairie Mountain. You can go to the Moose Mountain Ice Caves. So the Moose Mountain gas field is associated with that mountain, but it also has all of these ice caves throughout it. So it's a pretty phenomenal hike itself. You can go snowshoeing. So there's a whole bunch of snowshoe trails and biking trails throughout the area as well. And then it is quite close to the mountain. So Nihani Ridge is quite near the Bragg Creek Provincial Park. So there's a bunch of little hikes you can kind of go throughout there. And it's just a lovely area all around. But because it's not got so many outcrops, it's a little harder to put nice pictures of rocks in Bragg Creek, but it is a lovely foothills area. That is all I've got for this. So that's all about the geology as much as I could find of Bragg Creek. There's not a whole lot of work done in the area.
That's great. Yeah. So there's a question here. How large is Nihani Ridge? It looks like that's probably, it's the Cambrian sandstone on top. So it's probably Cardium Formation, right?
Mm-hmm. Just the elevation of it? I can Google it really quick.
Yeah. What's the elevation? Do you know? I could look it up here.
Just Googling it right now. It says 2.3 kilometers elevation.
What? Oh yeah, no, that's possible. Yeah, for sure.
Yeah, well,
from above sea level. Yeah, above sea level.
Yeah. Elevation of 415 meters, it looks like, from the base of the height.
Walk in the park.
Exactly. Easy stuff.
Wow, that looks gorgeous. Well, really appreciate that, Sarah. Are there any questions? Isam already had one question. Oh, Margaret has one. Margaret asks, the one I'm not sure if it has a name, but the one really famous ice cave hike is super fun. It's quite steep, but a really nice hike, and the caves are very cool. They're mountain.
Oh,
There's
that might be
also,
the Canyon Creek ice caves.
I don't know, Margaret. Feel free to turn on your mic, Margaret, if you want.
Yeah, the Canyon Creek ice caves are right near the Moose Mountain ice caves. It might be even on Moose Mountain. So it's good. Is that where you went this weekend, Margaret?
Construction by her house. Oh yeah, there's construction by her house, or she can't turn on the mic.
Oh, I see.
Did you go caving this weekend, Margaret? Cool.
Yeah, I would highly suggest going to Bragg Creek for anyone who's interested in more subtle hikes, not so much summit hikes of mountains, but if you're looking for like a nice, cool day trip, Bragg Creek's the place to go.
All hikes are awesome, right?
True, there's no bad hikes.
Right, that's what I think. Yeah, and scrambles are the most fun quite often.
Yeah, the dangerous ones.
Well, and the thing is, you can carry rocks and fossils back on a scramble. It's a little hard to do on a really treacherous alpine hike. So,
Exactly.
all right. Well, you need to unshare your screen,
Ooh.
Master's Candidate Biddle. And it looks like we have no more questions. So you can stay and watch for a while, or you can check out. You can do whatever you wish. I know we have a meeting later on in the week. So.
All right. Yeah, I think I'll check out now. But yeah, if anyone has any questions about Bragg Creek, email me. Come hiking with me.
Okay, that's
Maybe
great.
when this is over.
Yeah, I think people will be itching to get out by then.
Yeah.
Probably be winter by then. It'll be cross-country skiing.
2021. Yeah. All right.
Wait, I'm going to go ahead and share my. Oh, wait. Sorry.
Oh.
Thanks, Sarah.
Oh, no problem.
That's great. Thanks. Yeah, that's great, Eisen. Yeah. Yeah, good effort. So you'll send us those slides so we can put them on e-class, Sarah?
Sure thing. Yeah, I can do that right now.
Done. Okay.
All right.
And now we're back to our business. And there we are. Last week we were talking about the Mississippian, but the Devonian came up in the Franian-Fumenian boundary that is quite evident somewhere just below the Mississippian strata and in the upper part of the Devonian strata. And there it is. I found this paper from Nature Scientific Reports 2018 on the causes of the Franian-Fumenian extinction since this came up. And here I just highlighted some key parts. This is a paper that aims at trying to identify the actual timing of the Franian-Fumenian boundary. And here it says several possible causes for this extinction have been suggested, including extraterrestrial impacts, and large-scale volcanism. So both these things have kind of ideas have been around the block for a long time. And it was quite clear after looking at a few more papers that there's no definitive interpretation of what the conditions that led to the Franian-Fumenian mass extinction really were. You can go to the conclusion of this paper. And by the way, as these are all it's ways of showing lead uranium date systems and stuff like that, but they're just trying to pinpoint the age at which the uranium lead containing zircons can be determined to be, so that they can be associated with some type of process that you can also date, like because of the ashes in volcanoes and the fact that they carry zircons in those ashes. We can date volcanic ash very accurately. The same with impact features. There's mineralization associated with impact events that sometimes we can add fairly precise age dates to. So if we could get a date for the Frannian-Fominian boundary, and this is done in this case using zircons, and link that to other episodes that we knew happened around that time, say volcanism or say a known impact site, then you would say, okay, this will help us know what the cause of the effect was. And anyway, the conclusion of the paper shows that they come up with an age date, but surprise, surprise, the age date doesn't really match up anything. So here it says, thus, although there is no direct evidence of a coincidence between the extinction and large-scale volcanism based on the current geochronology, in other words, the age of the rocks that they just determined, major volcanic activity was so here, highlighting the need for further geochronological and chemostratigraphic data to confirm the existence or absence of major volcanic activity during the Frannian-Fominian boundary. And if you read earlier in that conclusion as well, there's no known impacts at that age date either, but we don't know of all the impact sites because that goes 370 million years back in the geological time record, and we can't see all of those impact sites. For example, the end of the Cretaceous impact site that happened in the offshore, we knew from ash layers far before we ever knew far before we knew where the impact crater was, partly because it was under sediments on the shelf of the Yucatan Peninsula. Yeah, extraterrestrial. Yeah, Sam. Yeah, extraterrestrial is a lot less exciting in in geoscience than it is in X-Files, that's for sure. So there you go. We don't know what caused the Frannian-Fominian boundary, so that's not so unusual. Today we're going to talk we're kind of doing a transition now from the Paleozoic and the Precambrian rocks into Mesozoic rocks, and we're entering a new set of tectonic controls and settings that greatly influence the geology of Alberta as we see it today, expressed both in the prairies and in the mountains and in the boreal forest and plains. So I thought today would be a nice day to segue into the history of petroleum geology in Canada with a focus on Alberta, because it's kind of a critical part of Alberta's history and certainly a critical part of our, well, what we off and on has been a good competitive advantage for Alberta. And I emphasize the off and the on for sure. So the history of petroleum geology in Canada. First off, a lot of you don't have a lot of experience in geoscience, although a few of you have good experience, but we'll just set up the frames of reference. Hydrocarbons include oil, gas, and coal. And up until the 90s, coal was the one that represented the most carbon that was being used from nature to produce electricity and energy. Petroleum became very important after the 90s, and natural gas is starting to supplant petroleum, but that depends where you are in the world. There's areas where natural gas is not used at all, and there's areas of the world where almost exclusively energy comes from natural gas. Interestingly, still about half of North America's electricity comes from coal-fired steam-generated plants, so we're not off our addiction to coal, and probably before we worry about any other source of CO2, coal's the one we probably need to address first. Feel free to type in any questions if you want. We mentioned this briefly in class, but I thought it was just worth emphasizing that hydrocarbons come from organic matter, and that organic matter usually comes from marine plants and animals that are planktonic, usually small animals and plants. It's microbially mediated at times, and you can get things like methane produced by or what we call biogas produced by microorganisms. But for the most part, we're looking at the decomposition and thermal maturation of kerogen, which comes mostly from marine plants. They, you might wonder why it's kind of funny. If you really look at the news, you'd think oil is yesterday's news, right? And that, in 5 years, we won't be using any oil at all. And I've yet to see a think tank projection that didn't have our oil consumption on planet Earth increasing all the way into the years 2050s. So I've never yet seen an exception to that. Almost everybody has us producing peak oil around 2040, 50, or 60, meaning that the hydrocarbon cycles or the use of hydrocarbons for energy is not nearly done. And if you look at this projection, here we have a 2016. Here, I'll just. Down at the bottom of the chart, you'll see 2016, 2025, 2030, all the way up to 2040, with the general predicted trend to be increasing throughout that time. Natural gas is predicted to do something very similar. And coal, well, it's basically flatlining, but what we would love is for it to go down. And I think most people would love for all of these energy sources to be used increasingly less and less. But none of the trends that we really see are actually indicating that that's going to happen immediately. And so oil and gas are really important resources to the world. And I think it's pretty clear that they're going to continue to be economically important driving factors for decades to come still. So, it's kind of interesting the perception that people have, because the idea that bioenergy and other renewables that might include wind, tidal energies and whatnot, and maybe things like hydroelectricity or nuclear can replace our energy use. But that's one of the reasons we don't predict oil and natural gas to drop off immediately. It's because there's only a fixed rate at which we can develop these renewables. And so these hydrocarbon resources are here to say, now this is a full disclosure thing. This diagram is made by the Canadian Association of Petroleum Producers. But I'm being very sincere when I say I've never seen a diagram like this that didn't in general convey exactly the same information, which is oil and gas increasingly being produced and used over the next 20 to 30 years, with the other energies increasing modestly to substantially as well. So that's why we're still interested in oil and gas in Alberta, and that's why you hear, discussion of the premier, well, no matter what you think of him, and not just the premier, industry, people who need work and stuff like that, really pushing for pipelines. So that's why. Energy consumption has persistently gone up over time. On this chart, you see the North American energy use over time, the Asian Pan-Pacific energy use over time, and these energy consumption curves certainly show why up until 2018, really it's up to about 2015 or so, the price of oil and gas more or less kept going up steadily. Other parts of the world, like Europe, are pretty stable. Europe's embraced the use of renewable resources more than most other sectors or areas. And so they've done very well at flattening their energy demand curve for at least 10 or 12 years now. And we mostly all know what oil is. It's hydrocarbon chains, gases too. So methane are short, small hydrocarbon chains. And once you get up to about, carbon chains of 8, 9, 10 long, you start to develop liquids. And the more carbons in that chain, the more viscous or gooey that liquid becomes. And so this is really oil. In this case, on the left, you just see liquid forms of oil that are actually pretty pure in this case. This graph is telling us that this is primary energy consumption. Who is this, Eisen? This is primary energy consumption. Yes, so Asia does use the most energy in the world, but not the most energy per capita. Does that make sense? Canada still uses more energy per capita than China, for example. Canada is 8th in the world, believe it or not, in our energy per capita use. It's not very good. Oh, I don't even think we're even 8th. I think we're probably per capita energy use, we're probably one of the least efficient countries in the world. It's partly the weather, but that's not the only thing. And I'll remind you that oil has a geological occurrence. And because it has a geological occurrence, it means there's geological parameters that can be predicted. And if you understand how to predict those parameters, you can predict the occurrence and distribution of oil and gas. And that's the whole point of geology when it's applied to oil and gas. It's for the most part identifying where there's more. Now, that's petroleum geology. Not all geology is petroleum geology. So this diagram I chose because it shows there's what we talked about here in class. Maybe I'll change that color. This shale rock here is a seal. And the seal, in large part, it contains the reservoir, okay? This is the reservoir. The poorest part, the porous part of the rock that can hold oil and gas resources. And somewhere below all of this is the source rock. And so we have things that we can predict from a geological point of view. The distribution or presence of seal, the distribution of reservoir, the structure or stratigraphy that can form a trap. And that's what we see here in this image, a pump jack that's producing from an anticlinal or antiformal trap. There's other types of traps that we'll talk about later. This is a more traditional view of an oil and gas play. There's even a couple mining and petroleum engineers in this course, and they'll know very well what we're trying to display here. But it's a conventional reservoir. It's the way we used to hope to find oil and gas. And nowadays, there's other occurrences of oil and gas that don't depend in the same way on a trap or a seal, and that includes shale gas. And shale gas is a rock that has such a low permeability that economic fluids, meaning oil and gas, are trapped in the pore space. Because for fluids to move in and out of a rock, the permeability has to be high enough that the fluids can move through it. And as you get to smaller and smaller pores or pore throats, the fluids have trouble moving through it. So what industry discovered back in the early 2000s, about 20 years ago now, and this was mostly a company called Devon Energy down in Texas, working out of the Woodford Basin down in Texas. And they found that you could make these large fracture networks in the rock by by injecting enough water, which is incompressible. So water doesn't expand. It exerts massive force when you push it into a rock under great deals of pressure. And they bring the pressure of the water up literally thousands of kPa, tens of thousands of kPa, until the rock literally breaks. And the rock breaks in these fracture planes that the water floods into. In with the water are some chemicals to help loosen up the pore throats of the rock, and also something that's called a proppant. A proppant are these grains that we put in it, usually glass or sand spheres, quartz spheres, that are pushed into the fractures. And then when you release the pressure of the hydraulic action, then the fracture can't close, and it holds the fracture open. Just think of fracturing the sand and the shale and filling it with loose sand, and it holds the fracture open. And then now you have these great surface areas that you can draw fluids from, and your effective permeability of the whole formation is much, much higher. And you can think about it this way: if you took a coffee bean and you boiled it, you would never get all the caffeine out, would you? I mean, maybe you would, but it would take time, weeks or months. But you grind a coffee bean to a medium or fine grind, and you can get all the caffeine out of it in seconds. It's the same coffee bean. What's the difference? The difference is surface area. Fracking makes surface area in the rock. And yes, that's the famous fracking. The fracking is, and these fracture networks are pretty extensive. They can extend from the borehole tens of meters. They do so in a radial fashion, and they increase the surface area of the rock along these sections of horizontal drills for hundreds of meters. So you increase your surface area of the reservoir by tens of thousands of times. And of course, people don't necessarily like fracking because there's a concern. What happens if your fracture reaches the water table? Well, now you can have these economic fluids contaminating your water, and nobody really likes that. So I mean, you can ask a whole bunch of questions that we probably shouldn't follow up on here, like, can fracking be done safely? Well, I suppose it can. Is it always done safely? I don't really know the answer to that. I'd say we know there's fracking incidents that have done damage or been deleterious to the environment and to some groundwater tables. But is it always an environmental issue, or does it always compromise the local groundwater or surface water or drinking water to an area? No, not necessarily. But yes, there's something to all that. Any questions? Your generation has, okay, this is a price chart for oil. It's all been presented in 2020 dollars. So February 2020 dollars. It's the most recent data I could get. And you can see that it shows a range of relative today of about $20, sometimes a little less, up to almost $160. These are US dollars, so at least I think they're US dollars. Well, I would imagine they're US dollars. It's from yeah, it's from an American source. And you can see that at least from the 40s up into the 70s, there was a long period of stability, and then the price goes up all of a sudden. And that price peaks out in 1979 at $130 relative to today. And that caused an economic recession. It was related to stagflation, where you have inflation rates and a decrease in consumer demand so significant that the economy crumbles. And so you have falling prices as a result of stagflation. And what caused this price to go up in the first place is, by the way, this is when OPEC gets going. So these are the OPEC establishment years. So OPEC is starting to drive the bus for the world price of oil. And they have the most oil, so that's their business if they want to do that. And then throughout the 80s and 90s, we had relatively low prices. And then we start to see global demand going up around the 2000s. And from the 2000s onwards, we're mostly up in a way. And so for the last, 15 of the last 20 years, it's been pretty good times. There's been highs and there's been lows, but overall it's been an economic boom for Alberta in particular, because, especially early in the 2000s, America and a lot of other companies like Statoil in Norway, BP in Britain, Total in France, saw Alberta and the oil sands as very attractive targets for economic targets, because they were very stable. They represented a very politically stable source of oil that you could depend on. It has very predictable daily production rates out of the oil sands, and also it's seen as socially responsible oil. But that all turned on their head by about 2010, where environmentalists became increasingly frustrated by heavy oil in the McMurray Formation and things like the McMurray Formation. And so you start to see all of these companies that came in because it was politically comfortable oil in Alberta, it became environmentally uncomfortable oil. And so a lot of those big international companies left. And so Alberta's had its own problems with companies leaving and stuff like that, but also there's been a global drop in oil demand that has something to do with global economic issues. And for sure, it'll go back up one day, but how Alberta will be affected long term is a good question. This is how we expect oil production to progress. This is a kind of a fun curve. It was invented, or at least conceived of, by Hubbard, peak oil theory. And his theory was that you first make all of your discoveries, and then you produce following. There's a lag time between producing energy and discovering energy. And so that's what he's proposing here. And indeed, to one way, shape, or form, this is USA data here from the 1950s up, it's before that, 1920s until the year 2000 or so, kind of shows the discoveries over time, that this is the discovery curve here, and that the production curve followed that. And we've seen tailing off from the 70s onwards in North America. So it's interesting that production picked up again in North America. And that has everything to do with these technologies we were talking about. The technologies of fracking, horizontal drilling, the advent of mining for oil in Alberta changed what we could produce. So we kind of challenged this Hubbard curve, where now, because we've got these massive resources in Alberta and other places like shale oils, where we kind of unlinked the discovery production link association a little bit. But I digress. Here's the real point. Canada's energy sector accounts for 10% of the gross domestic product, so about 15 billion, and it's ranged in the last 10 years between 14 and 20 billion dollars. So that's how much money the oil and gas industry means to Canada. So it's basically depending on the year, it's usually the largest or the second largest sector of our economy. Where does it all start? Spindle's Tops in the USA, not in Canada. It's Texas. And it was one of the first important oil fields in North America. And it was actually associated with salt diapurism. And this salt diapurism was the result of these Jurassic salts on the Gulf Coast. So these are salt. And what happens when you bury salt under kilometers of strata and you heat it up a little bit, it becomes very ductile and it forms upwards into diapirs. And so what's shown here are these diapirs. And these diapirs are not just offshore on the Texas, Oklahoma coastlines, but also onshore. And if you go onshore, that's where Spindletop was. And Spindletop was this salt dome. And what happened over the salt dome is, look at the limestone here. The limestone is folded, right? So there's a fold there and a fold there. And as a result, you have an oil water contact within this the Spindletop dome. And that was it was very close to surface, so you could drill it with this very old technology. And it was changes in drilling technology and exploration technology over time that led to us exploiting ever deeper and deeper resources. So it all kinds of starts with Spindletop, and there's some nice anecdotal stuff available from the U.S. Geological Survey that relates to Spindletop. So if you want to learn more, you can for sure. One of the first oil fields in Canada, though, was there were two pretty early. There's one in Ontario, that's where they actually named the community Petrolia. And Petrolia was discovered in the late 1850s, where a man, James Miller, began to develop some properties that he'd purchased and basically dug a water well, and he struck oil. And so there was enough oil that was seeping into these karst structures, and I can explain that it actually caused about a 20-year oil boom in the area of Petrolia. And I guess that's why they named it Petrolia when all was said and done. So I'm not going to get into this because this is Ontario stratigraphy, not the point of the course. But here you can see that there's limestones. They very nicely indicated the limestones here for us and dollostones. And what's happened is they've indicated zones of karst, okay? So karst are these sinkholes that form hang on, there. Karst are these sinkholes that form when salt or carbonates collapse. So basically meteoric water or atmospheric rainwater gets into the groundwater infiltrates, it exploits fractures in the rock, and it starts to dissolve things. Things like salt dissolve like crazy. And so what you have here are Silurian salts. The Silurian salts basically dissolve, and the limestone collapses into them. And the limestone that collapses into them in these brown zones becomes rubbly, its permeability goes up, and so oil can flow up through that limestone. We'll draw the oil in green as we should, and the oil migrates up through these fractures into the oil and gas reservoirs there, well, oil reservoirs. And so that is the anatomy of Petrolia and Canada's first oil field. And interestingly, remember, these are water wells dug by hand. So the depth of the oil finds themselves were not that deep. Some were as little as 20 meters. Here they show a scale of 200 meters on this geological interpretation, which seems a little much to me, but they might have later on developed later uh, later they might have started using drilling techniques, manual drilling techniques, to get down to some of the deeper oil reservoirs. So this is in Ontario, and I never actually said that anywhere. Oh yeah, Oil Springs, Ontario. I love those old pictures. Eh? That's cool. Moncton had a pretty old gas field too. I used to work out in in New Brunswick, and it was really interesting working on this gas field because the gas field still supplies Moncton today. So they've had this gas field that they discovered 111 years ago, and it still is the main energy source for the city of Moncton in New Brunswick. And associated with the Moncton gas field are also other things called oil shales, which the New Brunswick government gets really excited about every 20 years or so and launches a new study into how they're going to develop their oil shales into a hydrocarbon energy resource. But they've never done that. And here we talk about lamasites. These are just um, keratin-rich fine-grained rocks. You don't need to worry about that. Usually it's marine keratin, like algal keratin that we're talking about. And notice that they're Mississippian in age. So this is really the New Brunswick stuff. And there's even, this is where they were mining from the Moncton gas field some of the oil shales, because they would try to boil up the oil shales to liberate the oil that was in it, a fairly light oil, and so they would mine it and try heat it up and get the oil out. There was energy they could get. This here is called albertite, this mineral here. And albertite is a mineral that's formed by heating up the keratin, but not heating it up to the point of no return. And you can still actually take albertite and dissolve it with solvents and get kerosene out of it. So albertite was mined as well to make kerosene in the area. So that's one of the reasons they mined there. One of the first gas fields in Canada was in Medicine Hat, and this was Alberta's first recorded natural gas discovery, occurred in 1883. And that was from a water well, and that water well was being operated by the Canadian Pacific Railway. What they would do is they had water wells, and then the train would pull up to the station. Because these were steam trains, they would heat coal, and the coal would cause a phase change in the water. The water would change from liquid water to steam water, and then you could use the expanse of that process to drive an engine. Well, that's how a steam locomotive worked. But you needed water routinely to do that. So they had water rigs all along the railway from Eastern Canada all the way to Vancouver. And this ended up being one of our more enduring natural gas fields. The Medicine gas field still is important for its gas production today. It feeds most of Medicine Hat, its energy, and it's an incredible little gas field because it just keeps producing and producing and producing. And there's a postcard that commemorates its discovery. I got that from the archives of the Glenbow Museum. And it's a gas well at Bow Island, Medicine Hat, where they had a bit of a blowout because they encountered gas in strata shallower than they expected to. I've done some work on that. It's an interesting one. One of the first oil discoveries goes back to Waterton, and we'll talk more about that a little bit later. But there's a nice story in this book that's by George Mercer Dawson. Well, it's not by George Mercer Dawson. It's about George Mercer Dawson by William Chalmers. And Dawson was a Canadian geologist and scientist who was one of our first leaders of the Geological Survey of Canada. And here, Kootenai Brown, kind of a prospector in the area, was engaged as a guide and a packer by the eminent geologist George M. Dawson. And he asked me if I'd seen oil seepages in the area. And if I did see them, would I be able to recognize them? He then went into a learned discussion on the subject of petroleum. Subsequently, some Stoney Indians came to my camp, and I mixed up some molasses and coal oil and gave it to them to drink, and told them if they found anything that tasted or smelled like that to let me know. Sometime after, they came back and told them about the seepages at Cameron Brook. And interestingly enough, those seepages at Cameron Brook become Alberta's first crude oil well, and it's right in the middle of Waterton National Park, a place where you can go visit. Good light oil. It was produced for a few years. There's still potential production under Waterton National Park. That's another story. I don't think that'll ever happen. But a really interesting story that George Mercer Dawson, way back in the 1800s, was still coming out west and understood that oil and gas were an enterprise worth pursuing as far as a geological resource goes. And then there's the oil sands. Man, the oil sands are in the news all the time. Usually it's bad news, but it's still an amazing story. And the oil sands are Cretaceous. So we're going to talk about the geology of the oil sands, a bit more detail next Wednesday. But these are large deposits, and we'll get to just how large they are in a few minutes. They're thick. They're 100 meters thick in places, 130 meters thick in some places, and they're very extensive. We can mine them, we can steam them, and we get a lot of oil out of them. And they're the largest single oil deposit on the planet. It's just unfortunate that it's all degraded heavy oil, and some of it is even what we would refer to as ultra heavy oil. Discovered really by Peter Pond in 1788. And it was really characterized by Sidney Ells of the Geological Survey of Canada, who worked with the energy part of the Geological Survey of Canada. He was really an engineer. And they sent him up here to look at the oil sands and try to understand if they had an economic potential. And he worked on oil sands for 20 years, and he did a substantial amount of excellent work on the characterization of that deposit. It's a superb mining engineer, without a doubt. But it's not until the 70s, 60s, and 64 we think it becomes commercially viable, and then we get permission to produce it using mining and steam techniques. Today, we produce about 2 million barrels of oil a day from the oil sands. That's about 1/40th of the world's energy requirement from those mines alone. Sidney Ells actually wrote a paper about using the bitumen for paving, meaning you could just go mine it and pave the streets with it. And here's some experimental pavement that they were trying with the bitumen. They just went and mined it right out of the riverbanks at McMurray, and then they laid it down and packed it down. But it wasn't very durable as a bitumen and as a pavement, and so it never really caught on. It wasn't economic either. There's Sidney Ells. Sidney Ells, I guess, I mean, he looks like a tough dude. And he probably was. They were working on the Athabasca River, all these mosquito and black fly ridden rivers that were associated, little tributaries in the McMurray Formation, like the Firebag River, the Steep Bank River, and a river named after Dr. Ells, the Ells River. And quite often they were carrying they were portaging canoes. They were dragging the canoes upstreams against the shallow waters for kilometers on end. I mean, they worked so hard to understand that deposit. And then a really important U of A link to the Alberta oil sands is Dr. Carl Clark, engineer from the Faculty of Engineering, became, I mean, to this day, one of the University of Alberta's most famous former faculty. He basically invented the process that's used today at Syncrude and Suncor to separate oil and water and sand economically. And there's streets named after him. Like down in Research Way, there's a Carl Clark street or boulevard. There's buildings named after him, and certainly the U of A is proud to have him as a former colleague. This is what it looks like, an outcrop. It's amazing. This is all oil sands. Vertically, you're seeing there about 65 meters of stratigraphy, meaning from the top here to the Devonian limestone here, there's about 60 meters of strata. And you can see all of this is sandstone. So this is all sandstone. And the reason it looks gray and black is because it's all oil saturated. So it's like a fossilized oil reservoir that's exposed by rivers. And this river here is the Steep Bank River. You can't get to it readily. There's no road there. We normally helicopter it to get there. And this is the Alberta geology. Now we're starting to see, okay, so you've studied things like the Mississippian, the Devonian. Here we have some of the Cambrian and Precambrian appearing way down there. And you can see the foothills are here. Fort McMurray is here. So Fort McMurray here. We'll put the foothills here. And so we could put Edmonton right around here. And that's not a bad cross-section of Alberta. It's made by Mike Ranger in his 1995 PhD thesis, based all on subsurface data. So it's a real cross-section. It's not a cartoon. It's actually made of measured real data, but has a big vertical exaggeration. And now here's the map of the McMurray Formation. Okay, so what are we looking at? This is Alberta's DLS system, the Dominion Land System, townships and ranges. Each one of these here is, so if you took one of these squares, they're cut into 6 by 6 like that. Each one is a mile square. So 6 miles by 6 miles squares. In other words, each of these squares is 10 kilometers by 10 kilometers. This is all McMurray Formation strata here, shown as an isopath, meaning a thickness, where the darker, hotter colors are thickest, more than 100 meters, and it goes down to thinner, colder colors. So the main part of the McMurray Formation, where the reservoir is right along that trend, where it's variably 40 to 120 meters thick. But, okay, so that's big. That's a lot of reservoir, and it's mostly filled with oil. Now let's just compare that to England. Here's 2 maps at the same scale. And the same scale shows that the oil sands, if they were in England, would cover most of the country. Okay, so this is not a small oil deposit by any stretch of the imagination, and it's about, well, I'd say cover about 35% of England's entire area, which is stunning, right? Any questions right now? Okay. And here, if you want to go to the Athabasca oil sands, they've got a discovery center right on the southern edge of Fort McMurray. And it's well worth going there. They have a lot of the old equipment, like the bucket wheels, like we see right there. They have a lot of simulations and whatnot inside. It's actually a super interpretive center. And the interpretive center will take you on tours to the edge of the mine sites too. So that can be worth doing if you're curious. And you learn a lot about how oil sands are mined. And, even if it's horrifying to think of the scale of these mines and stuff like that, I think there's still something educational in seeing how it's done and informing yourself about the realities of the mining exploitation and how it affects the environment. So yeah, well worth doing that, that's for sure. Turner Valley we covered already, so I'm not going to cover that again. I'll point you towards the Turner Valley um, gas plant interpretive center, where you can actually go there and you can experience Alberta's history. It's actually a super cool spot to go. The old Turner Valley gas plant that was operating in the 30s is abandoned now. It's all rusting, but you can pretty much walk on site and poke around and get super cool pictures, photographs of these old facilities. And so you can go right to the Turner Valley location and have a look around. And that's the same with Leduc. We talked about Leduc already. I said I couldn't remember how many dry holes they drilled before they made the Leduc discovery, but it was 133 dry holes that Imperial Oil drilled before they hit Leduc. And this was, remember, I told you about the D1, D2, D3 things, and the D3 was D2 and D3 were the economic ones, and they never ever drilled deep enough to hit the D2 and D3. So that was that was why they never made the Leduc age discovery earlier, because they were just stopping drilling just a little short. There's a lot of famous fields in Alberta that are mostly stopped now. Simonet is just produced for a little bit of gas now. It's mostly blown down. Ante Creek's all but done. K-Bob's all but done. Swan Hills, still a little bit of production there, but you know, Swan Hills was a growing concern in 1971. That's when it was reaching its peak production, because in 1971, my whole family, my dad packed our family up in the car because he had a job in Swan Hills, and he hauled us all to Swan Hills to live for the muddiest, most coldest, most miserable year of my life. While we lived in Swan Hills, I go back there every so often. It's actually really pretty, but back then there was no paving on the streets or anything. It was like a frontier town. It was the fastest growing community in Alberta, and it was a real boom town. Sturgeon Lake, this is where the family farm is. Goose River is done. Redwater's done. Caroline's not done. It's coming. But in Leduc #1, think about this, stopped producing in 1974. Leduc #1 stopped producing in 1974. That is 27 years of production. 320,000 barrels of oil. That's crazy. There's a song you can go to for fun. I was going to play it, but we don't have time today, so won't be on the exam anyway. I showed you this map already, so, but I wanted to get to this anecdotal. There's this film night that they used to have at the Glenbow, and they sometimes had these industry stories that were presented there. And here, this one I liked, Leduc #3. It's about a blowout. The well had barely punched into the main producing reservoir a mile below the surface when a mighty surge of pressure shot the drilling mud up through the pipe and 150 feet into the air. As the ground shook and a high-pitched roar issued from the well, the mud was followed by a great dirty plume of oil and gas that splattered the snow-covered ground all around them. Drillers pumped several tons of drilling mud down the hole, and after 38 hours, the wild flow was sealed off, but not for long. Some 2,800 feet or 850 meters below the surface, the drill pipe had broken off, and through this break, the pressure of the reservoir forced oil and gas into the shallower formations. As the pressure built up, the oil and gas were forced to the surface through crevices and cracks. Geysers of mud, oil, and gas spouted out over the ground in hundreds of craters over a 10-acre area around the well. From Peter Mackenzie Brown. Like, my God, can you imagine the scene? Talk about learning the hard way. And back then, we really didn't have the technology to be able to predict or understand when you were going to have a blowout. Like, it was actually pretty inexact science. And we're better at predicting blowouts now because we know more about geology of Alberta and its subsurface, and we know more about what type of formations contain these high pressures of gas and oil that can cause a blowout. But we still do have blowouts. The most recent blowout in Alberta was only 5-6 years ago, and but they used to be common. They used to be an annual thing. now it seems to happen more like once every 10 or 15 years. So why did they keep drilling? You'd think by the time they got 100 dry holes, they would have given up. I know, 130, like who was approving that budget, right? I really don't understand. Well, I mean, they knew Turner Valley told them they had source rock and reservoir rock, and they just wanted to find this Devonian stuff that they'd found in Norman wells, right? And they just, yeah, they just didn't. You imagine in today's dollars, that's probably the equivalent of wasting about $250 million, at least. It's probably more than that. It's probably more like $1 billion that they wasted. So good question, Stephen. Here, this puts the Devonian bit into perspective, okay, where we have these different production curves. These are all different Leduc reservoirs. Leduc, the main one, near Edmonton, Redwater, close to Edmonton, Bonnie Glen, Wizard Lake, Atchison, Westeros, Sturgeon Lake, Innisfail. These are all huge. Look at the numbers there, right? Like the Bonnie Glen, 520 million barrels of oil. Holy Dinah. But these are the production curves. This is a percentage. So when you reach that line, you produced all the oil. And what you can see is from 1960, somewhere down here, up until about 2000 here, pretty much all the oil is produced by the time we reach 2000. So your generation just missed out on all that. But you got to enjoy the boom of the last 20 years associated with heavy oil. And you can go see Leduc #1. There's a little pump jack sitting there, and there's a little plaque, little fence around it. It's easy to get to. It's a Canada historic place. I totally recommend you go there, especially if you're interested in oil and gas at all. It's pretty cool to see the site of one of the most important energy discoveries ever made, and certainly the most important in Canada. There's Mitsu. We talked a bit about that. Mitsu, remember, I'll just show you the paleogeography map. Here's the paleogeography map, and we can see that here's what we now call the Peace River Highlands, right? The Peace River Arch. So it's a topographic high during the Devonian, and there's sediment that is shedding off of these highlands. They're making these delta deposits. And what you can see here to the right of this is kind of a close-up map of what the main Mitzhu deposit looks like, or main Mitzhu reservoir looks like. And just to be clear, this is Lesser Slave Lake, I think, right here. So that's Lesser Slave Lake. And that's just to position you where all of these sandstones are in the subsurface. So here's Mitsu oil field down here. You can see it's pretty big. It's about 50 kilometers long by about 20 kilometers wide. It's what we call a stratigraphic trap, meaning it's not folded. It just means that the porous rock interfingers with non-porous rock, and it doesn't go any, and so it seals itself in. And yeah, this is really the Mitsu field. Nothing too much to talk about. We talked about it already, but I knew that the structural versus stratigraphic trap thing had to be addressed. So let's think about that. A structure trap might be a fold where the porous rock is folded underneath a less porous rock. So let's say this is the porous rock here, and this is the shale here. Then the structural trap would trap the oil or gas within the confines of that geological structure. And there's different types of structural traps. faults like Turner Valley is a combination fault and fold trap, right? We saw that nice cross section last week of that. And if we wanted to look at what a stratigraphic trap is, you need to use your imagination in an entirely different way. You know that rocks are laid down in layers, the law of original horizontality and lateral extensiveness. But, you know, just because it's sandstone here doesn't mean that it goes sandstone forever. Let's say that you're going from shallow water to deeper water, then this sand will interfinger with the deeper sediments, and we draw it like that. That's what we mean when we're interfingering. And so we have shale here, and if we're lucky and there's shale on top, then the stratigraphic trap will develop in behind that lithology change. And so there we have our stratigraphic trap. So that's the difference between a structural trap and a stratigraphic trap. And then a very classic stratigraphic trap, and it's one that we'll talk more about when we look at the Cretaceous of Alberta and Western Canada. But the Cardium is a really important one because it's the Pembina oil field, which is one of the largest, most prolific conventional oil fields that we've discovered in Alberta. And this was a sandstone that was very much like what I've drawn here. It was a sandstone that interfingers with shales. And, you know, something you might glean from this section here is, look, the structure trap is defined by its spill point. So the structure trap here can only fill up to that spill point, meaning there's a limit sometimes to how big a structural trap can be. That said, that limit can be pretty crazy. But think about the stratigraphic trap. The closure is infinite, right? It goes as long as you can keep filling it with oil, you have a reservoir. It doesn't go forever and ever like that, because sooner or later, the oil's buoyancy pressure will push so hard against the low permeability rocks that oil will start to flow through them, okay? But you can have, I think that the long and short of it is that stratigraphic traps can be aerially very large. And really, the McMurray Formation is, as much as anything, a stratigraphic trap. Oops. That said, there's some very large structures too. And so oil and gas deposits can be really, really big. So where's the Pembina field? It's near Drayton Valley. So basically due west of Edmonton, about 110 kilometers or so. It's Cretaceous in age, has oil and gas from it. And the main formation is the Cardium Formation, which we'll talk about on Wednesday next week. But there are other formations that contribute. So this goes back to 1953, and we still produce from the Cardium today, and we still explore in the Cardium today, although we use different technologies like horizontal drilling and fracturing to develop parts of the Cardium that 30 years ago were not economic, but today we can make them economic with these new techniques. So some recent graduates of the University of Alberta, both in engineering and in geoscience, are at work on the Cardium today at CNRL. And the discoverer of the Pembina field is Arnie Nielsen. And I mention him here because he's an alumni of the University of Alberta. And he was a big supporter of the University of Alberta and donated lots of money to the University of Alberta because he became super rich. He was a geologist who was the discoverer of the Pembina field, and he became ultimately the vice president of Mobil, which is unusual for geologists to do. Usually those are business people and engineers, but not exclusively. And there's an article here that is an asynchronous assignment for your exam. Okay. So you can read about Arnie Nielsen and his various discoveries, but great U of A hero and one worth knowing about for your final exam. You can see the Cardium Formation in the mountains all over the place. Easiest place is to go to CB Dam just west of Calgary. There you can walk down and around and you have beautiful exposures of this shore face sandstone that have fossils in it, like ammonoids, ammonites. It has bioturbation in it. Lots of cool sedimentary structures, and it happens to be really, really pretty there. But you do have to mind the dam. They raise, they maintain the level of the dam very carefully. So quite often they'll open the dam a little bit every day, and water will go up a half a meter or so. So you got to be aware when you're there. But that's a really nice spot to go see the Cardium Formation for sure. And then one of the more recent discoveries, I think of it as recent. It's not anymore. I mean, they were exploring for the Hibernia field, which is offshore Newfoundland, all the way into the 60s. But it wasn't until the 80s, well, I guess late 70s, early 80s, that they started making substantial discoveries that could be made into that showed it to be economic, and ultimately they started producing oil and gas out of Hibernia by the 90s. And just notably here, in 1982, the Ocean Ranger was lost. This was a rig, an offshore rig at the time, state of the art. Its deck was the size of 2 football fields. 88 people on board, lives were lost. They only recovered 22 of the bodies. The others were gone. And it was one of Canada's really notable maritime disasters. It was actually, it was because they didn't understand the conditions they were building the platform for. So they were building a platform. In fact, I think I pulled up a picture of it for you. Let's see if I can find that. Ocean Ranger, where are you? I'll just do it again. So the Ocean Ranger. Oh, here it is. I'm just going to share the screen. There we go. So this is the Ocean Ranger here. 30 years, this article is from 2012. You can see the deck here, it's quite large. They didn't understand what they were making this for. This has 2 pylons, one on each side, that you can control the buoyancy of the structure by putting water in or taking water out. And the water is pumped in by quadrants, and you pump water in and out of these quadrants and balance it precisely how you wish, which should have worked very well. But you'll see the control centers here, right? Well, the Ocean Ranger was subjected to a winter storm that was so severe the waves were smashing through the windows of the control deck. And the control deck, ultimately, the windows failed and salt water got into the controls of the deck, and they lost the ability to evacuate or pump water in or out of the pylons, and so they lost buoyancy, and down she went. All right, and so that was the sad story of the Ocean Ranger. But the Hibernia itself is a big discovery of oil. There's 1.5 billion barrels of oil there, and it's Cretaceous. It doesn't matter. We're not going to talk much about the geology of Eastern Canada, but I included a cross section here to show you kind of the various stratigraphic units that are associated with the Jeanne d'Arc Basin and the Grand Banks. You can think of this as being related to the rifting that severed Pangaea in two, and sent North America going one way and Asia and Europe going the other. And these normal faults were part of that. These normal faults were part of that. Were part of that pulling apart of Pangaea, and then the normal faults made for a number of structural traps that you see in these various areas here, and that's kind of the story of all of these offshore. We always refer to these Grand Banks plays as Hibernia. Hibernia is one field. There's Terra Nova field. There's the Hebron field that was not developed. I don't think it might have been. I can't remember. White Rose is developed out there now before this slide was put together. So that's the story there. And then I really dig this diagram here. At first you look at it and you must think, well, what the heck am I looking at, right? And what this shows you really quite cleverly is a year. So these are a chronological data set on the bottom. And then what you see is you have these different colors, and each color comes on. Now there's anything, all of these colors here are before 1966, 62. And then any new color added after is production from a stratigraphic, from an oil, from it really is a stratigraphic interval, but we'll call it an oil field, when it started producing. In other words, we start getting blue production here in 1962. We start getting this pinkish red, purplish red, I don't know, production. It appears to come on in about 1964 or 65, okay? And then you can see over time how the cumulative production goes up and up and up. And you can see we hit our peak production in Alberta in 1974. 1974. I was 9 years old. And in I accidentally closed that map. Eisen says the map looks like my background. It really does, hey? It's so psychedelic, but I just love what it really tells us. So peak production, 1974. And then pretty scattered, but very gentle decline all the way up to about 2004. And it's interesting. So throughout the 70s in North America, we always saw this as doing this. That was what was predicted, right? But you're seeing this. Whoops, no, we should redo that. But you're seeing this, and in fact, if you projected it another 5 years even. And I think, yeah, by the time we get to the last 5 years, by the time we hit 2015, we're up to 2 million barrels, right? So in fact, we end up being even higher than our 1974 peak. So this is going, it's trending upwards for the next few years, right? And then you can see all these different productions coming on, like these are heavy oil deposits coming on throughout the 90s as we get better and better at producing heavy oil. And you even see in here some, although maybe not much yet, but you're starting to see also the impact, I think, of, uh, of shale gases and shale oil and stuff like that. So just kind of food for thought. I really get a kick out of this graph. But it's too bad you don't have a code to show what field it is that comes on. That would be really neat. But for instance, this whole peak here, this is mostly Devonian, right? By the time we hit 1975, we're mostly dealing with peak Devonian oil. And then we have other unconventional resources in Western Canada. And those unconventional resources today, I didn't put a slide together about them because you can get kind of lost in the whole shuffle of this. But the unconventional resources, there's two really big ones. One is a Triassic one that we're going to talk about on Monday, and that's the Montney Formation. And the other one is lower, and it's the Devonian Duvernay Formation. So these unconventional resources are unattractive because they need fracking. So let's put bad and good. So from an environmental perspective, fracking. And fracking is not just the risk of contaminating water, but the other thing is it uses a lot of water, right? It takes several Olympic-size swimming pool volumes to frack a well. So fracking is bad because of the fractures and the water use. So these are major issues. And I think the good side of it, though, is that it's widespread. It's easy to predict in occurrence. And it really is widespread, easy to predict in its occurrence, and I guess it relates to abundance. If we wanted to keep producing oil and gas for the next 150 years because of shale oil and shale gas, we probably could easily, but I think God help us if we do. And also bad. Each of these unconventional wells cost lots and lots of money. And that changes the economics of an oil and gas play. It used to be that, you could have a great idea, you could, arrange financing with 2 or 3 interested parties, use other people's money. If you raised $180,000, you could go drill a well and discover your own oil and get rich. Well, the cost of getting started in these unconventional resources is tens of millions of dollars, right? And so the problem is this is for big companies only. And it makes the little oil companies a lot less able to compete. And something that really worked to Alberta's advantage over the last 100 years has been this tradition of entrepreneurs without a lot of money in their pocket being able to go have good ideas and discover oil and gas. And those days are going away. And the problem with this is then when it's just big companies that can take advantage, it's just the rich getting richer, right? That's the problem with it. So it's losing its, I'd say it's losing some of its social attraction that it would have had for a long time ago. I just wanted to show you a map of Alberta here. This is from the Geological Survey. I put it on E-class for you. It was done in 1970. So these are all the mostly Devonian and Cardium and Viking reservoirs. And we haven't talked about Cardium or Viking yet, but here you can see Edmonton is right here. So there's Edmonton. Grand Prairie is up there, and the border of Alberta is here. So you can see the distribution of oil and gas. And it shouldn't surprise you that if you were to look at the basin orientation, the basin all dips in this direction, right? Meaning it gets deeper along the trough of it. And you really see that in the oil and gas distribution too. There's a geological and a burial control on the oil and gas reservoirs. But I love this map because it really shows you, when you really look at it, just how pervasively distributed oil and gas deposits are in Alberta. And then this map here, blue is oil and gas and red is gas only. Okay, so those are all fields. That accounts for about probably half of all the fields that have been exploited since the 1920s now. And then also shown on here, the Cold Lake oil sands, which weren't developed yet at 1970, the McMurray, Athabasca oil sands. This is Pelican. And these are the Peace River oil sands here. These are all being developed now. And so we can add all of this and all of this, all of this to the area of reservoir. Look how big those are. Those are massive stratigraphic traps, and that's why they're so interesting. Yeah. Anyway, it's getting a little on 4:06, and I didn't give you guys a break today, and I feel like I'm probably going to run out of steam. There's a little bit of asynchronous reading for you to do, and I'll let you go ahead and do that. So I will end the class now, but I gladly take questions. Dr. Johnson is teaching on Friday. Stephen, you're going to do that live, right?
Yep, Murray, I will be broadcasting live.
Delightful. Okay, that's perfect. And then, yeah, I don't think I have anything else to add. So the asynchronous reading is just the Cardium Pembina field. Yeah, that little article about Arnie Ness-Eisen. Okay, that's it. Okay, you can all start checking out. I don't think we're going to say anything important now then.